Hello, this is my lab for my 4-bit adder for lab section '06 for Susan Nachawati. I'll begin by showing you my code for my half adder. So we have our two inputs, or 2 bits, and our output C, which is going to be our carry if it goes over, and our output S, which is going to be our value. And a half adder has a XOR between the A and B with the S as the output, and an AND gate with A and B with the carry as the output. And I'll go to the schematic and show you. This is the schematic for the ripple, but since the half adder is inside, I'll show you what that looks like. So this is the half adder. There's that AND gate with inputs A and B, and the XOR gate with inputs A and B as well. And as you can see, the XOR gate has the output S, and the AND gate has the carry output. And then we're going to move on to our full adder. Just give it 1 second. But the full adder will also have inputs A and B. Full adder adds 4 bits. Excuse my computer being slow. Yeah, so these are going to be 2-bit inputs right here. And then the carry in input as well, if we have a connecting adder. And then we also have output S and our carry output if it goes over 8 bits. Or 15, sorry, not 8. And then right here, I'm going to wire my my first adder, and then the other one, and wire the sum as well. Here I am defining my 2 half adders to make the full adder, and then an OR at the end for the carry out. And then I will go into my schematic to show you that. So as you can see, I have 2 half adders in this full adder right here. And then we have our carry out on that first half adder going to this OR. And then we also have the S output from this first half adder going into our A right here. And then we have our B value coming from our carry in, which is a product of our carry out, or some of our carry out, my bad. It's our carry in going as for the B, so A plus B, and then it goes through this half adder right here, gives us a carry out, and then our value right there. And then we have our ripple carry, if my computer would like to show you. Here it is right here. So we are going to use A 3 times in our ripple carry on different occasions, different adders, same thing with B, and our outputs are also going to do that. And then with our ripple carry, we are going to have 4 full adders with all these inputs right here. And take a look at the schematic. you can see I have, this is blown up, but I'll just do that. So you can tell that I have 4 full adders right here, and the full adders are made with the half adders. And so this A is going to this one, and this one as well, and this one as well, and finally this one. This B is doing the same thing, and the carry in for all of them as well. And then I have my, I'll run the simulation for you so I can show you what the, oh, it's already run. Yeah, so this is what my timing schematic looks like for the ripple carry. As you can see, it has the values in a decimal form right here, showing you exactly what it's doing. And then I can pull up my output to show you what the machine is doing. So on the first randomized one, I have a input for A in decimal, I have 4, and then an input for B, which is 1. So this would be 0, 1, 0, 0, and this would be 0, 0, 0, 1. Or excuse me, this would be yeah, that's what it would be. Sorry about that. And then you can see that 4 plus 1 in our adder is going to be 5 with no carry because it does not go over 16. 9 plus 3 is going to be 12, obviously, with no carry. 13 plus 13 is going to be 26. And so our output is going to be 10 because it is 10 over 16, 26. And this has a carry because it went over that value. 5 plus 2, 7, and so on and so on. These two have carryouts because they are greater than 16. And yeah, that is my 4-bit ripple ladder. Thank you.